And as a consequence of all the previous assertions, it's something that figures on the lecture notes that you must have downloaded from Espace, and it's not written on this one. Yeah, I mean, it's the most essential one. I had forgotten to write it in my first draft. So we have the following theorem. Well, if A is a square matrix of order n, so n rows, n columns, we have the following equivalence. A is full rank. Consequence of the rank nullity theorem means that the rank of A is n, all right? So that's the dimension of the space, so of my domain and of my image. So the null space has dimension 0, so that's equivalent. If A is full rank, then A has a kernel, a null space reduced to only the 0 element of Rn, of course. And of course, I've got both properties. The null space one gives me injectivity. The full rank one gives me surjectivity. It means that A is a bijection, and in terms of matrices, A is invertible. Okay, that's the beauty of that. When you've got a square matrix, it's enough to have the corresponding application to be injective, right? To be also surjective, and then to be bijective. Okay, but that's only for linear maps when the domain and the image have the same dimensions. Okay, finally, let's go to something that is really, I would say, Gilbert Strang novelty. I believe it really brought that that following image, so that you see that we will have four fundamental spaces that are related to some matrix. So let's see. Now let's go back to typical rectangular matrix, n rows, p columns, and we know, you know, that what the rank is, we would assume it has rank R, so R is smaller or equal to p, of course, because it's the dimension of the column space. All right, so smaller or equal to n, sorry, that's dimension of the column space. Okay, so what have we seen as fundamental sets yet? We have seen the column space, which is a subset of Rn, so maybe we should A goes from Rp to Rn. Okay, so the column space lives there while the null space lives here. Okay, so we've seen the column space, we've seen, well, the row space. The row space belongs to Rp. Okay. Why? Because it's the one that's going to make linear linear combinations, right, of items in Rp that they sit in the rows, and then it has, we saw that's one of the theorem, it has the same dimension as the column space, and then we saw the null space. Okay, so the subset of Rp2, okay, that has going to have dimension p minus r. That was the rank nullity theorem. Okay, now let's see what is the row space that we have. Actually, it's going to be, if you transpose your matrix A, the column of A transpose are the rows of A. So the row space of A is the column space of A transpose. Okay, so maybe I should write that. The col space of A transpose is equal to the row space of A, and vice versa. Okay, the row space of A transpose is equal to the com space of A, right? And so yeah, it's not the inverse, it's just the transpose. If A goes from Rp to Rn, A transpose goes from Rn to Rp. Okay, just take one of the rectangular matrices that we've seen maybe earlier and look at what the AT is going to be. So, according to the rank nullity theorem, we can just also express the rank nullity theorem for AT, right? So for A transpose, we have that the dimension of its domain, so which is n, should be equal to the dimension to its rank. And so we saw that its rank, well, dimension of its column space would be equal to the row space dimension of the row space of A, which is the same as the dimension of the column space of A. So it's still the same R, right? Plus the dimension of the null space of AT. Okay, I'm just applying the rank nullity theorem, so that we have our fourth fundamental subspace, the null space of AT, and all of them together, they are going to build on one side RP and on the other side Rn. Okay, that's what we have here. Okay, so your matrix A goes from Rp to Rn. That's using A. You take X in Rp, get Y in Rn. Anything that belongs to the null space is going to be sent to, well, all of this is going to be sent to that particular value, 0. Whereas all of that, what's remaining in RP that does not belong to the null space, is going to be sent to linear combinations of the columns, so the column space. So all of that is going to be sent to this. So what's all right? So A is the process that takes all your RP space and sends it to, well, we have to take the 0 and that column space. So what's remaining in Rn? What's remaining is that one. And that one happens to be, well, we've just seen that if you consider A transpose, you've got the same IDs, and that one just happens to be the null space of A transpose. So I would say this is the space that's going to play the least importance, but however, it's you have to be to understand that this is something that completes the column space in Rn. Okay, the column space of A is just one part of Rn, and what's remaining is actually something that belongs to the null space of AT, so that if you apply the A transpose, so A transpose goes from that to this is going to be sent to that 0. Okay, and one very last thing that we have to show is that you've got these mentions of perpendicularity here. Well, maybe we should prove that. And we will even call that, rather than perpendicular, orthogonality. And you remember that X and Y are orthogonal if their dot product is equal to 0. Okay, that's when you've got a dot product. In terms of vectors, so there are vectors of the same size if you want to make the dot product, and that's it. But another way to write the dot product if you are afraid to not see the dot, well, many more ways. One way that I will affectionate a lot is that kind of stuff, but it's a bit heavy now. We don't really need that. But the vector way to write this is to write that it's Y transpose times X as the usual matrix product. Okay, you've got a row vector times a column vector, so that's the usual matrix product. All right, so let's prove that the column space of AT is actually orthogonal to the null space of A. What do we mean by saying that two subspaces V1 is orthogonal to V2? For any V1 that belongs to V1 and any small v2 that belongs to my second space, then the dot product of the two is equal to 0. Well, any two pairs of vectors, one in the first space, one in the second space, are going to be orthogonal. Okay, that being said, let's prove that the column space of AT is orthogonal to the null space of A. In other words, that's the row space of A. Okay, orthogonal to the null space of A. Okay, but so that RP is actually really made of two pieces that are orthogonal. Okay, so what I mean is that the RP that we have here is made of those two pieces that are actually orthogonal. So let's take some Y that belongs to the column space of AT. Okay, so to the row space. What does it mean? It means that there exists X such that AT times X, and this being the usual matrix vector product, is equal to Y. Okay, now, so this thing, of course, belongs to RP. Okay, so now let's take some, I don't know, Z that belongs to the null space of A. And let's do the dot product of that Y and that Z. Okay, if I'm doing that, it's just the same thing as saying, well, let's write it with the vectors matrix multiplication, the usual. So row vector times column vector, so Z transpose times Y. Okay, now let's use the fact that Y actually comes from A transpose times X. And you know that matrix multiplication being associative, I can rewrite that as this times the X. And you know that this is AZ transpose times X. Okay, the transpose of a product is a product of the transpose, but in the reverse order. Okay, but what did we say? Okay, can you see where we're going? What space does Z belong to? Null space of A. So that means that this is equal to 0 just simply because Z belongs to the null space of A. All right, so this whole stuff is equal to 0. All right, so we really have that those spaces are orthogonal. And of course, for the other side, the Rn side, it's exactly the same thing because actually it's exactly the same kind of things that are happening, but with A transpose. Okay, so here it is. All right, thank you very much.